Welcome to the team. I'm your senior software architect, and I am so pumped to have you all here for this explainer on system design. Today, we're setting the stage for building highly maintainable, professional-grade Python code. We're not just trying to make things work, right? We want to make them work beautifully, predictably, and reliably for the long haul. Let's get into it.
All right, I want you to start by picturing a pretty high-stakes scenario. What actually happens to our e-commerce app if our main payment provider just changes their API tomorrow? Like, out of the blue, they push an update and rename a core function. Well, if our code base is tightly coupled to their specific system, our entire checkout process breaks instantly. Boom. Revenue stops dead. Customers are stranded. It's a nightmare. And this is exactly the problem we're going to solve today by learning how to enforce some architectural standards.
Okay, let's dive into this. Here's our roadmap for today. 1. What is abstraction? 2. The car engine analogy. 3. The payment gateway problem. 4. Refactoring with the ABC module. 5. Rules and best practices. And 6. An architect's quick knowledge check. Section 1. What is abstraction? Hiding the complex implementation. So, abstraction. At its core, it's just the concept of hiding complex implementation details from the user and only exposing the essential interface. Basically, it's about separating what a system does from how it does it. Look at it this way. As a user, or even as just another part of our code base, I shouldn't need to understand the millions of lines of code making a system work under the hood. I just need to know how to interact with it safely. And from an architectural standpoint, this is absolutely crucial for scaling. It lets multiple developers work on different parts of the system at the exact same time without constantly stepping on each other's toes, because the core interfaces stay the same even when the underlying code is evolving. Section 2. The car engine analogy. Driving without knowing the mechanics. This brilliantly illustrates the difference between an interface and an implementation. Imagine learning to drive in just a simple, everyday car, like a Ford EcoSport. You learn the interface, right? The steering wheel, the brakes, the gears. You don't need to understand the complex thermodynamics of how the engine actually fires to drive down the street. But later, maybe you achieve a dream and get to drive a supercar with a massive high-performance V8 engine. Because the interface, the steering wheel, and the pedals is exactly the same, you can just get right in and drive. That super complex implementation of the V8 engine and the sophisticated clutch mechanisms, it's completely hidden from you as the driver. We absolutely must build our software the exact same way. Section 3. The payment gateway problem. The danger of tightly coupled code. Now, let's bring this back to our code. If we're building an e-commerce checkout page and we hard-code our purchase logic directly to a specific provider, let's say Razorpay, we are tightly coupled. And guys, that is a massive operational risk. If Razorpay decides to rename their pay method to Pay, or if we just want to switch to a cheaper provider, our entire codebase crashes. Why? Because we relied on their specific implementation details. What we really need is a plug-and-play architecture, where payment gateways are completely swappable. By building against a standardized interface instead of a specific vendor's code, we dramatically lower our risk and totally future-proof our app against sudden third-party changes. Section 4. Refactoring with the ABC module. Implementing strict interfaces. Let's move to and see how this builds in Python. Now, if you've written in languages like Java or C#, you know they have a strict interface keyword built right into the language syntax. But Python, it was originally built for functional programming. The object-oriented features kind of grew over time. So out of the box, Python developers often rely heavily on assumptions rather than strict enforcement. To fix this and establish rigorous design standards, we have to make a deliberate architectural choice to bring in a built-in module called ABC. That stands for Abstract Base Classes. Using this module lets us explicitly define strict blueprints that our application absolutely must follow, which keeps rogue code from sneaking into production. Okay, let's walk through the exact code to build this interface together step by step. Step 1. At the very top of our file, we import ABC and the abstract method decorator from the built-in ABC module. Step 2. We create our new parent class, let's call it Payment Gateway, and we pass ABC into its parentheses so it directly inherits from it. Step 3. We define our required function, let's call it Pay, and we stack that abstract method decorator right on top of the function definition. Finally, step 4, and this is literally the most crucial part. Because this is just an abstract blueprint and not an actual concrete implementation, we don't write any logic inside the function body. We simply use the pass keyword. We are just declaring what must exist, not how it actually works. By refactoring our code this way, we create a beautiful, flexible hierarchy. Our abstract parent, payment gateway, enforces the absolute standard,
any child class must have a pay method. So if we create a concrete RazorPay class, it implements pay. If we decide to swap out RazorPay and build our own Telesco Pay integration, we just create that child class and it also implements pay. The absolute magic here is that our core purchase application, the actual checkout logic, doesn't have to change at all. It doesn't care which provider you use. It just accepts any valid gateway object, knowing with absolute certainty that the pay method is guaranteed to be there.
Section 5. Rules and Best Practices. Why strict enforcement matters.
Now, what's really interesting about this slide is understanding why we choose this specific design pattern over standard Python polymorphism, which you'll often hear called duck typing. The old duck typing philosophy basically says, hey, if it walks like a duck and quacks like a duck, it must be a duck. In practice, this means Python just passes an object in and assumes the method is there, right up until the exact millisecond it tries to call it. If you pass a generic object into your checkout and assume it has a pay method and it doesn't, your program violently crashes mid-execution right as the customer tries to buy. But with ABC enforcement, we get a massive safety net. If a child class tries to inherit from our payment gateway, but the developer forgets to define the pay method, Python throws an error immediately at instantiation before the program even really gets going. It's a total game changer for structural safety.
Section 6. Architect's Quick Knowledge Check. Testing your understanding.
All right, I want you to think about this carefully based on everything we've covered so far. What happens if we write gateway equals payment gateway in our code? Like if we try to create an object directly from that parent abstract class, what will Python actually do?
No way around it, you will get a massive type error. It'll explicitly tell you, can't instantiate abstract class payment gateway without an implementation for abstract method pay. And I really want to emphasize the word instantiate here. Remember our earlier car analogy? An abstract class is just a concept. It's a blueprint. You cannot actually drive a blueprint of a car, right? You have to manufacture the actual physical car first. In programming, you can only instantiate the concrete child classes that provide the real implementation logic.
So the crucial point is you need to internalize these 3 cardinal rules for abstract classes. First, you absolutely cannot create an object of an abstract class. Second, any child class that inherits from an abstract base class must override and implement every single abstract method. Third, the abstract methods in the parent class cannot contain their own logic. You just use the pass statement. If you lock these rules into your workflow, your architecture is going to be robust, scalable, and just rock solid. I want to leave you with this provocative thought as you head back to your desks today to review your current projects. Look closely at the modules you're working on. Are your system dependencies tightly coupled, leaving them totally vulnerable to breaking at any moment? Or are you taking the time to build adaptable, plug-and-play interfaces that will completely future-proof our code base for whatever comes next? Use abstraction, build smart interfaces, and always code for the future. Thanks for joining me for this explainer on system design.